Alright, so this video is going to talk about measurement and uncertainty. You're going to have to bear with me just a little bit. One of the problems with using the document camera for video problem solving is I'm left-handed. That's this one right here. So the camera really likes to focus on my left hand instead of the writing. So I will adjust it as necessary. You can always pause the video to copy something down that you want to add to your notes. And if you have any questions, go ahead and mark them down so that we can address them in class. One of the things that's the most important to remember about measurements is that there's no such thing as a perfect measurement. Every single measurement has uncertainty. But it's important when we're doing measurements in the science laboratory that we try and get the most accurate measurement that we can. So we should start with talking about the term accuracy. Accuracy more or less just means correctness. It's the idea of getting the answer perfect, getting the measurement perfect. It's correct. In kind of a direct term, it's the idea of hitting the bullseye. That is accuracy. The more accurate your measurement is, the more correct the number it gives you is. The more accurate your laboratory procedure is, the more correct the results are going to be. That's something that I definitely want you to think about, because having an accurate laboratory design is going to give you accurate numbers. If your laboratory design is not so hot, then there's going to be a problem with your accuracy. And a problem with your accuracy means that your data might not match up with what theoretical data should be. And that's going to be something that you would have to discuss in your laboratory analysis. But accuracy is correctness. But no matter how accurate you have a value, there's no such thing to perfect. Precision is more exactness or consistency. Precision is a property of the instrument that you're using and the experiment that you design. You can design an experiment that will give you very precise or consistent results. Or you could design an experiment that kind of has answers all over the place. One way of looking at that would be, let's use our target hitting concept. Alright, if we have a target, you could design an experiment that gives you answers all in the same area. That would be a really consistent experiment design. On the other hand, an imprecise experiment design might give you answers all over the place. And that's kind of a bogus design. You ever design an experiment like that in my class, I would expect you to do a complete redesign. It doesn't matter if one of your answers is completely perfect. With that level of inconsistency, you're just not on the right track. So it's a property of the experiment that you design or of the instruments that you use to experiment. So another way of looking at that would be to consider a measuring device like this one. And if you have this measuring device, you could potentially have an incredibly precise, exact measurement. All right, let's take for consideration the idea of measuring a tiny little pencil against this tiny little ruler. See, there it is. It's a pencil. I swear it is. It's beautiful art right there. So you could have, we'll say we have a centimeter mark, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, and from this perspective, looking at it this way, we could say that our little tiny pencil comes in just under 4, and we'll say that these are centimeters. So our little tiny pencil is just under 4 centimeters. And depending on who you asked to read this measurement, you might get the answer, it's 4 centimeters, it's 3.8 centimeters, it's 3.7 centimeters, it's 3.9 centimeters. So your consistency is a little bit off there because not everybody who reads it is going to give you the same answer. That's a property of this measuring tool that we have right here. If, however, we change the measuring tool so that it also has millimeter marks on here, now we can take a look, and we're going to get a little bit closer in on it. And now we can clearly see that this pencil right here, our tiny little imaginary pencil, is coming in at right at that last millimeter mark. So it's coming in right at 3.9 centimeters. And anybody who reads that is going to be able to give you that value. No matter who reads it, they're going to see, oh, it's coming in at that last mark. That's 3.9 centimeters. This has now become a property of the measurement tool that we used. It's more exact. It's going to give more consistent readings because we can see more clearly where our value is. So that's precision. Accuracy is correctness. Precision is exactness. Which brings us to uncertainty. Every single number, like I said, has uncertainty in it. So we're going to take a look at what that means when we look at a number. We're going to use the example 8.8 centimeters. I like this number. It's the number in the book. You took your notes on it. Hopefully you made a note that how these numbers are affected by the principles that you're looking at. The number 8.8. We can assume, looking at this number just based on where the decimal is and the fact that the number is truncated after the 8, we can make an assumption that this number has an uncertainty of plus or minus 0.1 centimeters. All right, the reason we can make that assumption is if this number had an uncertainty of plus or minus 1, then we wouldn't be saying it was 8.8. We'd be saying it was 9, because if the number was 9 and plus or minus 1 was the uncertainty, that would cover a range from 8 to 10, and 8.8 would fall in it. Because we said 8.8, that means that the uncertainty is plus or minus 0.1, which means that this number is somewhere between 8.7 and 8.9. Right, that's where our number falls in. And we know that because it's truncated in the 10th place. So this is the most accurate of the measurement. And because there's uncertainty in the measurement, it gives us this very small range. We could say under most laboratory circumstances that our uncertainty falls under that decimal place. And depending on our measurement tool, we could say it's plus or minus 1 from that place or plus or minus 2 from that place. A plus or minus 2 from that place would mean 8.8 means between 8.6 and 9.0. So that would be a plus or minus 2.2 on that measuring scale. And depending on your measurement tool, depending on where your uncertainty lies, you're most often going to be choosing in that digit a plus or minus 1 or a plus or minus 2. Here's where we're going to kind of take a look at what a 0 at the end gives us. So we have 8.80. It's the same number, right? It's still 8.8, but now we're saying that this number is 8.80. So in this case, our uncertainty is actually going to be in the hundredths place. So I'm going to stick with the plus or minus 1 for that place, and I'm going to say that 8.80 means between 8.79 and 8.81. So we can see here that our uncertainty, our plus or minus 1, is actually happening in the hundredths place in this number. This is much more accurate. It's actually on a magnitude on an order of 10 times more accurate than the number above it. That's what our uncertainty means. More or less, anytime you're recording numbers, anytime you're recording data, we need to make sure of this primary principle. And that's that your numbers must represent the amount of uncertainty in the measurements that you took. So 8.8 means between 8.7 and 8.9. 8.80 is going to mean between 8.79 and 8.81. Here's where you have to be the judge. You have to determine, based on the tools that you used to make that measurement, you have to determine which of these is more appropriate. Can you only predict that it's somewhere between 8.7 and 8.9? Or is your measurement device accurate enough that you know for sure that it's not going to be smaller than 8.79 and it's not going to be larger than 8.81? You need to indicate your uncertainty with either a plus or minus, like we've done here. We could say 8.80 plus or minus 0.02. Right? This is indicating our uncertainty. This would tell us that we're pretty confident that the correct measurement here is between 8.78 and 8.82. So that's how we can indicate uncertainty. A lot of the time, our laboratory tools are going to give us some sort of a value of uncertainty. And so here you're going to take a look at conceptual example 1-1 from your textbook. All right, conceptual example 1.1 is, I think, kind of a fun one. I've always liked this particular conceptual example. It's actually a conceptual example that I took a look at and I solved in my first analytical classes for physical science in college. More or less, it's the study of, well, how well do you trust your friends? You see, you've fallen onto the possession of a really snappy looking diamond. I mean, look at that diamond. It's a good looking diamond. And you show it off to all of your friends. But what happens is that your friends also like that diamond, and so they say, hey, bro friend guy, do you mind if I borrowed that diamond, and I would really, really love to show my family this diamond and how awesome you are because you have this diamond. And you love your friend, but for some reason you kind of think that your friend's a little bit of a suspicious character. So either you need to lay off of being suspicious, it's your friend, dude, or maybe you need to pick your friends better because why are you hanging out with sketchy people? Either way, you make a decision that you're going to let your friend borrow the diamond, but you're going to do a little bit of lab work before you let him borrow it. You're going to take your diamond and you're going to put it on a balance. All right, and let's take a look. So this is your diamond on a balance, and you put your diamond on the measuring tool, and you get a mass of 8.17 grams. And so you go ahead and you record in some official document. All right. Your official document is your My Diamond document. You write that the mass is 8.17 grams. But if you read the manufacturer's disclaimer on the scale, it says that the scale has an uncertainty of plus or minus 0.05 grams. So let's consider what that means. That means that uncertainty, plus or minus 0.05 grams, more or less tells us that you could have a true mass that is 8.17 grams plus that uncertainty, right? Because that uncertainty could go above or below. And that could also mean that your diamond actually has a mass that's 0.05 grams less than 8.17. So that gives you a range. This scale is able to give you a range, and it promises that your diamond has a true mass between 8.12 grams and 8.22 grams. And we can clearly see how this is done. Just taking our calculator. And we could say 8.17 plus 0.05, that's the uncertainty. That gives us our maximum in the range. And 8.17 minus 0.05, that gives us the minimum in our range. And so that's where this range right here came from. So you record on your very official My Diamond record keeping paper, and then you let your buddy borrow your diamond. The next day, your diamond is returned, and everything looks to be in order. It looks like your diamond. It smells like your diamond. It tastes like your diamond. I don't know why you know those things about your diamond. But you put it on the mass, and you get a mass of 8.09 grams. And you're like, not cool, bro. I thought we were friends. Because you see, you're thinking about this range right here. You're thinking, if you would put your diamond on the scale and gotten a mass range that fell in the range of 8.12 to 8.22 grams, then you would know that you got your diamond back. But 8.09 grams clearly falls outside of that range. But I think you're just going a little too fast. And for some reason, you're really looking to incriminate your friend. So let's go back to the superficial analysis of your diamond. We're going to put an official recording, and we're going to take a really close look at this value before we press criminal charges against your friend. Remember that the scale promises plus or minus 0.05 gram accuracy. And your diamond should have a mass that falls under the range of 8.12 grams and 8.22 grams. Well, let's take a look at the returned diamond, because you see the returned diamond has a mass of 8.09 grams on the scale. However, that number has an uncertainty of plus or minus 5 grams. So we're going to we're going to find the minimum and the maximum of the range. So first we'll do the minimum. 8.09 minus 0.05 grams gives us the minimum of 8.04 grams. That's the smallest that this returned diamond could be by mass on this scale. The largest that this diamond could be on this scale is 8.09 plus 0.05, and that gives us 8.14 grams. So let's think about this. Compare this range up here to this range down here. This is your diamond that you had. The mass falls somewhere in this range, which means that the true mass of your diamond could be as low as 8.12 or 8.13 or 8.14. The diamond that was returned to you falls under the range of 8.04 to 8.14 grams. Remember, according to this range right here, your diamond could have a true mass of 8.14, 8.13, or 8.12. There's overlap in these two ranges. Therefore, the likelihood that your friend somehow grifted you on a diamond is actually pretty low. Because the ranges overlap, this is likely your diamond. And if you're going to get yourself all worked up over a diamond like this, then maybe you should get a more accurate scale. Because, for sure, the two of you can totally stay friends. If you can trust your friend with a diamond, what can't you trust them with? So that kind of gives you a really good overview of what uncertainty means in measurement and how to use accuracy and precision in an experiment and how to make sure that you're reporting numbers as correctly as possible.